the electricity use jumps to more than 50 gigawatt hour, which is about 0.1% of New York City's total annual electricity use. So driven by the booming AI industry, an unprecedented expansion of data centers is taking place in today's power grid. And this figure shows the actual and projected large load capacity in ERCOT's grid. As we can see, the large load capacity is increasing very fast, and will reach more than 200 gigawatts by 2030. This is phenomenal given that the current ERCOT's peak load is just about 85 gigawatts. And not only in Texas, the total US data center electricity use is projected to double or even triple within the next 5 years. As a result, the large data center load is emerging as the new large dominant load and is placing substantial stress on today's power grid. We have a recent review and vision paper on electricity demand and grid impacts of AI data centers. And in this paper, we summarized the key challenges from different timescales, including the long-term planning, short-term operation, and real-time dynamics and control. We have also proposed potential solutions from the perspective of power grid, AI data center, and also the AI users. If you are interested, you can scan this QR code to access our paper. And today I'm going to focus on the fast time scale dynamics and control of data centers. Large-scale data center is introducing significant challenges to power grid dynamics and stability. The first key challenge is the disturbance residue issue, because data centers, they are power electronics based, which are very sensitive to power grid side disturbances like voltage sag, which can lead to the tripping of the entire data center facility. For example, a large load tripping event occurred in Eastern Interconnection in 2024. So as you can see from this figure, this is the total system load curve in the Eastern Interconnection. And we can see that about 1.5 gigawatts data center load tripped within just a few minutes due to a fault-induced voltage violation. And similar for ERCOT grid, they have experienced more than 20 large load tripping events within the recent 2 years. So as you can imagine, hundreds of megawatts or even gigawatts large loads suddenly tripped from the system, which will cause a serious power imbalance and also the disturbance to the grid. So currently, the ISOs and utilities, they want to impose some requirements on the residual capabilities of large load. So for example, this is the voltage residual curve imposed by ERCOT, which means they need to follow this residual curve. Once there is a voltage sag or voltage increase from the grid, the data center facility cannot disconnect instantaneously. They need to stay there for some time. So for example, if the voltage drop to 0.7 per unit, data center should stay there for at least 0.5 seconds. So this is for the rest rule. The other key challenge is the false oscillation. As we can see from the left figure, this is the GPU power during the AI model training. We can see that the GPU power can fluctuate a lot. For example, from 0.1 per unit power to 0.9 per unit power within just a few seconds. So driven by the AI workload, AI data centers may have large and fast power fluctuations that can induce false oscillations in the power grid. In 2023, a large data center in the Midwest produced false oscillations. So this figure, the lower figure, shows the field voltage in a substation, and we can see that there was a 1 hertz false oscillation in the voltage induced by the data center power fluctuation. In addition to these two key challenges, we have other fast time scale dynamic challenges. For example, the grid interconnection with the grid control interaction with the data center, cascaded tripping, harmonics, resonance, power quality, and more. So then how do we address all those challenges introduced by the large-scale data centers? Before we get started, we realized there is a more fundamental problem. We don't have the model. As data centers, especially AI data centers, are emergent large load, we don't have the validated high-fidelity dynamic models of those large data center load. So this really motivates our project. In this project, our goal is to develop generic EMT dynamic models for large data center loads. Then we can use the model for simulation for studies to understand their dynamic behavior and the impact on grid. And based on the model and simulation results, we can generate tools, guidelines to address all those challenges in the fast time scale. So for this project, we have been focusing on two types of large data center load. One is the crypto mining load. The other one is the AI data center load. In Texas, we have about several gigawatts crypto mining load. This is kind of special in Texas. And you can think of the crypto mining load as one type of data center without UPS. So I'm going to introduce our models for these two types of large loads. Let's start with the crypto mining load. So this figure shows the typical electrical architecture of a crypto mining facility. So you can look at this figure from left to the right. It's connected with the grid and through a three-phase transformer to lower down the voltage to 15 volts. And then at each phase is connected with multiple crypto miner machines. This is a real on-site picture of the crypto mining facility, and they have hundreds of thousands of those miner machines in a facility. For each miner machine, we can model as this power electronic circuits. So it's connecting with the single phase AC voltage going through a EMI filter, and then we use a AC-DC rectifier to convert AC to DC. After that is a boost PFC circuits, power factor corrector circuits, to step up the voltage, and also make the power factor to be 1. Then is the DC link capacitor. After that, we connect with a DC-DC converter. Then it's connected with the minor processor. What we want to do is we want to replicate the overall electrical architecture and also the power electronics in our model. So this is we developed this EMT model for crypto mining facility to replicate the previous electrical infrastructure in PSCAT. This is our model, and if we look from the left to the right, it's first connected with the utility grid, and then through a Y delta transformer to lower down the voltage. We also have this power scaling module to scale up the capacity to hundreds of megawatts or gigawatts. Then is a delta Y transformer to lower down the voltage. At each phase, we connect with an aggregate crypto miner machine model. If we look into details at each crypto miner machine, it's modeled as this circuits. So we can see that from the left is connecting with the AC voltage and going through the EMI filter, going through a full bridge rectifier. Then is the PFC converter with the breaker and the PWM controller to modulate the control signal to the transistor, which is IGBT here. After that is connecting with the DC link capacitor, and then is we model the crypto mining power load as a constant power computing load. So this is the overall model for crypto mining facility, and it replicates the previous classic architecture of a crypto mining facility. In addition to that, in addition to the switching model, we have also developed the average model. What we do is we replace the high frequency switching devices using the controllable voltage and current sources so that we can avoid the high frequency simulation. In this way, we can greatly enhance the simulation efficiency. We have tested, they have very similar simulation results, but the simulation efficiency of the average model can be 10 times faster than the switching model. Also, we have also implemented the protection mechanism for the crypto mining facility. In this case, we have three protection mechanisms. The first one is the low DC voltage tripping mechanism. So if the DC link voltage is lower than a threshold, and for a hold up time, we will trip the miner. The other one is the over AC current tripping. So if the current from the gray end, the AC current is above a threshold, we have the over current tripping to protect the miner machine. Also, we have developed a user-defined voltage read-through curve. So for this module, user can customize the voltage read-through capability of their model. So then it can replicate, can be very flexible and adaptive to a specific miner machine. This is our EMT model in PSCAT for the crypto mining facility. We have also done the model validation using our lab tests and using the field testing data. So in Texas A&M, we have this power electronics and AI computing low lab. In this lab, we have the programmable AC power source. We can use this to simulate any power grid site disturbance. And we have this high resolution oscilloscope to capture the fast time scale voltage currents. This is the crypto miner donated by our industry partner, and this is the software interface we can use to adjust the setting for the hash rate of the miner. So for the lab testing, we have done several lab tests to validate our model. The first one is we increase the mining power from 1.5 kilowatts to 2.8 kilowatts. So this is the comparison between the lab test and our simulation results. The upper figure in red, this curve is the real experiments of the power. Because we increase the power reference, we can see the power is increased from 1.5 to 2.8 kilowatts within 50 milliseconds. And lower figure is our simulation results. You can see that our simulation results is aligned very well with the real experiments. So in addition, we have also tested the read-through capability of our model. So what we do is we simulate a gray voltage sag. We drop the gray sag voltage to 0.73 per unit. So the first figure is the AC side, the gray side AC voltage. We can see that the RMS value is decreased from 1 per unit to 0.73 per unit. And the second figure is the AC grid current, because it's modeled as a constant power. So with the voltage drop, we have the current increase. And last figure is the DC link voltage. For these three figures, the red curve is our simulation results using our model, and the red curve is the real lab testing results. We can see that the simulation and the real testing align very well. The case three is we continue to do the low voltage tripping testing. If we keep dropping the gray side voltage to 0.7 per unit for 2 cycles, so you can see from the first figure, the AC side voltage decreased from 1 per unit to 0.7 per unit for 2 cycles. And the second figure is the corresponding AC grid currents. The red curve is the simulation results, and the blue curve is the real lab testing. In this case, we can see because of the voltage drop, there is a current increase. And this current increase is over the threshold for protection. So we have a tripping event here. So you can see that after this tripping, the current from the grid, the AC grid current becomes zero. This means the facility is tripped from the grid. And the last one is the DC link voltage. In addition to the lab testing, we have also validated the model using the real events. So we get the data from ERCOT, and we have done this real DFR voltage replay. We just replay the real voltage measurements to the grid to simulate the events and to see what's the model response as well as the real system measurements data. So this is the results. The first figure shows the gray side voltage. This is the real gray side voltage from the real event. This is unbalanced gray sag, voltage sag at different phase. The red curve is the phase A, green curve is phase B, and blue curve is the phase C. We can see there is unbalanced voltage sag across three phases during this event. And then the second figure and the third figure are the active power response and reactive power response to this voltage sag event. And in these two figures, the red curve is the real DFR, real data from the DFR. The blue curve is the simulation results from our switching model, and green curve is the simulation results from our average model. You can see that they have a very similar pattern and they align well with the real field data. Okay, so that is the first part for dynamic modeling of the crypto mining load as well as the model validation. Then I'm going to introduce our AI data center load model. Again, so what we do is first, based on our conversation with our industry partners and some public information, we have developed this electrical architecture for AI data center. This is the architecture one. We have more architectures I will show you later. This is the electrical architecture for AI data center. You can look from the left to the right. First is connecting with the utility grid through the automatic transfer switch, and we also have the backup generation. Then is going through a step-down transformer to lower down the voltage. It's connecting with the UPS system. UPS system is essentially is the battery system. When there is a disturbance from the grid end, the UPS system will the computing load will be transferred to the UPS system immediately. Then it can last for tens of seconds or a few minutes before the backup generation pick up the load. In addition, we have this bypass switch. If the grid is in the normal condition, the power can just go through the bypass switch and to supply the computing load parts. After the UPS and bypass switch, we have the three phase. Each phase we have the power distribution units, then connected with the computing server. The computing server is modeled as similar to the crypto mining computing load. Is a PFC circuit to convert AC to DC, and then we have the DC-DC converter, then connecting with the GPU, CPU computing load. In addition, we have the cooling load and other load like the lightning. So the two key difference of the data center from the crypto mining facility, one is data center has this UPS system, and this is very important for the dynamics of a data center. In addition, for the load is not a constant power load. It should be modeled as some time varying load profile that can be all those data can be obtained through real testing. This will also induce the disturbance to the gray side. In addition to the first architecture, we have more architecture. So this is the architecture 2. This models a distributed battery system. In this case, we don't have a centralized UPS system. Instead, we have a distributed battery backup units for each server. In this way, they can enhance the reliability. Also, we have the architecture 3 and architecture 4. Architecture 3 is using a high voltage DC system. And in this case, we don't have the double conversion architecture. It's just use the AC-DC converter. Then it's connected with the high voltage DC link. Then is all those computing servers connected to the high voltage DC link. In architecture 4, is similar to the architecture 3, but here we use the solid state transformer for the power conversion. So what we want to do is we want to build our dynamic models in PSCAD and to replicate those electrical architectures. To do that, our approach is we use a bottom-up modularized approach for the model development. So what we do is we have developed this component library. For each key components in the data center, we have a module for that. So for example, we have both the switching model and average model for the rectifier, inverter, the bidirectional DC-DC converter, the PFC circuit, cooling load. And in addition, we have implemented all those protection, the load profile, and also the battery model for the UPS system. Uh, in addition, for all those components, we have implemented the controller. For example, we have the gray following control for rectifier, gray forming control for the inverter, as well as the battery charging and discharging control. Let me show you the specific the control design. For example, this is the gray following rectifier, which to control the rectifier. In this case, we have both. This is replicated as this module, and in this module, we can achieve both either the active power control or the DC link voltage control, and we also have the current limiter in this model. I will not go to too much details, and if you are interested, we later on I'll show you the user manual, and you can refer to our user manual for more technical details. This is the gray forming inverter, and in this inverter, we have implemented a gray forming control to control the terminal voltage of the inverter. In addition, we have implemented the frequency power droop and voltage reactive power droop. Also, we have this bidirectional DC-DC converter to control the battery charging and discharging for the UPS. And by the control, we can change the voltage, the output voltage of this converter that can modulate the charging and discharging. Okay, so overall, this is our EMT dynamic model for a data center in PSCAD. So from left to the right is connecting with the utility grid, and here we model as a voltage source. But if we have the detailed model from the grid, we can directly connect this module to the grid model. After that is a Y delta transformer to lower down the voltage, and then is another like a second transformer to step down the voltage. Then is connected with this one is the bypass switch connecting with the AC computing load. Also, we have this branch. This is going through a rectifier. Then is the inverter. Then is connecting with the AC load. And here we have a DC link capacitor. And for the DC link capacitor, we connect with the battery through a DC-DC converter. So this is a typical architecture of a data center. And in this data center, we have several operation modes depending on the grid side voltage, so that we can ensure the reliability and reliable high-quality power supply to the computing load. So this is for this we have both the average model and switching model. In terms of the simulation efficiency, if we simulate for 10 seconds and if we set the time step as 20 microseconds, the average model takes about 26 seconds. The switching model takes about 400 seconds. So you can see that the average model can accelerate the simulation a lot because it removes all those high frequency switching using the controllable voltage and current sources. And for a data center, it can operate at different operation modes, including the bypass mode, the double conversion mode, and also the battery backup mode, depending on the grid side voltage. Let me give you the examples. So suppose the grid side voltage is in the normal condition. For example, the voltage of the grid from the grid is about 0.9 to 1 per unit. This means the grid voltage is at the normal condition. And in this case, the data center will operate in the bypass mode. That means the power is directly going through this bypass switch and to supply the AC computing load. It's not going through the rectifier and the inverter. And also in this case, we can use the going through the rectifier and DC-DC converter to charge the battery if needed. But if the gray side voltage is getting worse, for example, if the gray side voltage dropped to 0.7 or 0.9 per unit, in this case, the power directly from the gray side is not qualified, is not as uh, has the high quality to connect with the AC load. In this case, the data center will switch to the double conversion mode. Double conversion means the power is going, we will open this bypass switch and the power will going through the rectifier to convert AC to DC, then going through this DC to AC inverter. Through this double conversion, we can still maintain the AC load interconnection points has a very good voltage, for example, close to 1 per unit voltage. Uh, in this case, the AC load is has the voltage supplied to the AC load is high quality, and also we can charge the battery if needed. And if the gray side voltage is keep dropping, for example, below 0.7 per unit, the rectifier and inverter just using the double conversion, we can not really maintain the high quality voltage on the AC load side. In this case, the data center will switch to the battery backup mode, and the battery is discharging to supply the AC computing load going through this path. It's going through the DC-DC converter and through this gray forming inverter and then connected to the AC load power. The mode switching between these three operation modes is critical for the data center response to the gray side disturbance and also their dynamics. So in our model, we have implemented and embedded the rest rule mechanism and all those mode switching logics to our model. So it depends on the gray side voltage. We have all those flow charts to control the model switching so that our system can switch among the bypass, double conversion, and battery backup mode depending on the gray side voltage. And in our model, we can achieve the voltage rest-through. We have embedded the voltage rest-through mechanism, frequency rest-through mechanism, also these three operation mode switching as well as the reconnection. If the gray side voltage is recovered to a good condition, we can reconnect the data center to the grid. Let me show you some simulation results using our model. So for this AI data center model, if we simulate a gray side voltage drop from 1 per unit to 0.7 per unit, the system will transition from the bypass mode to the double conversion mode. And here are the simulation results. So we can first look at the left figure. In the left figure is, let me use the, okay. So this is the simulation results when the gray side voltage drop to 0.7 per unit. We can see that this figure is the voltage. The blue curve here is the low side voltage. The red curve is the gray side voltage. We can see the gray side voltage is drops from 1 per unit to 0.7 per unit. And at this point, we have a mode switching from the bypass to double conversion. And during this event, we can see the low side voltage is still maintained at close to 1 per unit, even though the gray side voltage dropped to 0.7 because we have switched to the double conversion mode. So here, the second figure is the current. We can see the bypass current is jumping to 0 and the rectifier current increased to 2 per unit. That means the rectifier and inverter is picking up the load. Also for the power, this blue curve is the the power through the bypass breaker. The power is decreasing from 1 per unit to 0. And then the power from the rectifier is increased and more than 1 per unit because in this case, we are also charging the battery. So the total power is the load power plus the battery charging power. But in this case, the load power is still maintained at close to 1 per unit. So we have a reliable power supply to the load. The right figure also shows the power and the DC link voltage initially is dropped, but after the double conversion, it can recover to the close to 1 per unit. And we can see the battery SOC, the state of charge, is increasing, as um, in this case, we are charging the battery. The second simulation result is we keep simulate a voltage drop to 0.5 per unit. And in this case, we are going to switch from the double conversion mode to the battery backup mode. When we implement the voltage drop, here are the simulation results. Again, we can look at the left figure. So this red curve is the gray side voltage is jumping from 0.7 to the 0.5. If we do not do the mode switching, the AC computing load cannot be directly connected to the 0.7 or 0.5 per unit voltage. That will trip the AI computing load. But in this case, through the most transition, when we switch to the battery backup mode, we can still maintain the low side voltage at close to 1 per unit. Then if we look at the power, you can see that the bypass power is still 0. The rectifier dropped from the previous close to 1 per unit to 0, because in this case, the power is fully from the battery. So but the load is still maintained as the close to 1 per unit. If we look at this figure, this is also the active power figure. This green curve is the DC-DC converter. Means the power from the battery is starting from 0 and then maintained at -1 per unit. -1 means this currently is discharging. And the DC link voltage is initially is dropping, but then it's recovered by the battery control. We can also see the SOC of the battery is decreasing. Okay, so this is the simulation result. We can see our system can implement all those model transition as well as the voltage and current control. So this currently we don't have the real lab testing or the field testing to validate model, and we look forward to collaborate with industry to validate our model. And our EMT models for the crypto mining load and data center load I have just introduced, we have released open sourced and released these two models. These two models have been posted on ERCOT websites, and you can scan this QR code to access the model. You can download the user manual and PSCAP model. And here are our user manuals for these two models, one for the crypto miner load, the other one is for the data center. And you can find all those model details and how to use the model in these two user manuals. Okay, let's wrap up this webinar. So in this project, we have developed the high-fidelity EMT dynamic models for both the crypto mining load and AI data center load. The key features of our model is, first one is generic. You can adapt this model to some set-specific architectures or designs. Also is developed in a modularized approach. We have created a library of the modular components and control. So it's very flexible and can be adapted to some specific design. It's also pretty flexible. We have many user-defined settings and the model is in per unit. So if you enter the power capacity, it can automatically calculate the corresponding resistance, inductance, and capacitance, and it can scale up to the hundreds of megawatts or even gigawatts. Also, it's open source. You can download our model and user manual from the previous link. We also realized that the PSCAD is now widely used in academia, so we are also going to develop the MATLAB Simulink model for both the crypto mining and also data center. And in terms of the use cases, we can use the model for the grid interconnection studies, and also we can evaluate the grid impacts of the AI-driven workload. We can also use the model to study the grid stability, control design, also the data center electrical design. In addition, this EMT model is high fidelity. We can use this as the benchmark for other model developments, for example, the phasor model or the data-driven models and the validation. At last, I'd like to introduce our consortium on AI and large flexible load at Texas A&M. So this is a platform for connecting academia and industry to advance research and development in AI and large load. And this is the pictures from our on-site visits to the data center and our workshop. And you can scan this QR code to get more information about this consortium. Okay, so that is all for my talk, and thank you.
Yeah, thank you for the nice presentation. I think there are multiple questions in the chat. The first question was about in slide 33, why does the voltage drop so slowly instead of instantly and then gradually recover?
33. Okay, yeah, this in this slide is we run simulation, we simulate the voltage drop from 0.7 to 0.5 within 0.1 second. I think the voltage drop is not very slow. It's kind of because this the measurements. We talk to all those simulations. We talk with our like the industry partners. I think the voltage drop within 0.1 second for 0.2 per unit is not that slow, but definitely we can simulate a faster voltage drop to test the response of this model.
So my question, actually, this is the name, good talk. My question is mainly regarding how you simulated the voltage drop, because usually you would have a transmission grid, and then you will have an outage, and then you simulated the voltage drop. So then the voltage drop actually would be sharper, I think, or at least have a natural recovery process, because the system also have a voltage sensitive loads. And then this seems to be, are you just simply using a, how did, but basically this question drills down how you simulate the voltage drop. You just gave it a slope and then dropped it from the infinite bus?
Yes. So in this case, we focus on the modeling of the data center. Then for the gray side, we model as a voltage source, and then we simulate the voltage source voltage drop. But yes, if we have the EMD model for the gray side for the power grid, we can connect this module to the grid, and then we can run the simulation. But in this case, yeah, in the simulation, we just simulate using a voltage source.
Okay, so my second question actually related with this one. Do you have any internal impedance for the source, or just assuming it's all zero?
In this simulation, it's zero.
Okay, got it.
But in the previous case, we can also I remember we have added like internal impedance here, but here in the simulation we set at zero.
Okay, thanks.
Yeah, and there was a question about the link of the models in whether you can drop the link in the chat, but I think we are going to upload this recorded
For the
version
link,
in our YouTube channel. So yeah, I think yeah, Paris, you can refer to the videos we are going to upload.
yeah, sure. Let me just copy paste the link to the.
And another question was related to the load part. So there was a question about what type of load model is used for the IT load.
For the IT load, so currently what we model as a constant power load. But for the constant power, we can load the load profile. It can change over time. So here in the model, for this part, the AC load model we have is a module replicating the connecting with the PFC circuits and then goes through the DC-DC converter with a DC link capacitor, and then we connect with a constant power load. But we can input the load profile. So if we get some real testing results from the GPU testing or from some other experiments, we can input the low profile, and then we can simulate the overall system response.
Yeah, and I also had the similar questions, and they're all
Mhm.
multiple people um recording the questions. So, what is the difference between your data center load model and the recent PNNL data center model?
Oh, that's a good question. I have prepared a couple of slides for this question. I thought some of you may ask this question. We was doing we were doing this modeling work in parallel with PNIL, and the first author of PNIL model, Brett, also like regularly join our meeting, and we share his comments, and we communicate on how do we develop models. Uh, Overall, I think the overall architecture is very similar, and here are the key difference we have summarized. So we have different models for the battery cooling loads, the voltage ratio, and reconnection. For example, for the battery, we are using a more detailed battery model with the SOC dynamics. For the cooling, is rather than a equivalent resistance, we using the FOC inverter and also induction motor to represent the cooling load. We have also implemented a very comprehensive low voltage ratio and high voltage ratio, as well as the frequency ratio in our model. For the interconnection, we have both we can switch between the model between the voltage control and also the power control. So we can also implement the power ramping limits on the reconnection process. But in the PNL model, it only use the voltage control. So here are some details. We have the different battery model and cooling model. Basically, we have more realistic battery model and cooling load model. And for the model transition as well as the rest-through, here we can implement a rest-through curve similar to the curve imposed by ERCOT. But in PNL model, they only use a single point for the protection. Also for the reconnection, we can switch between the DC link voltage control and power control. So during the reconnection process, it's better to use the power control, uh, so that we can control the ramping up power, and we have also implemented the ramping up limits into the model. We can achieve the fast reconnection or the slow reconnection by changing the ramping up rate. Yeah, I think that's the key difference between our model and the PNL model. Yeah, thank you for the question.
Yeah, there are a lot of questions remain. So the another question from Prashana was there were two questions. So the first one is that would it be possible to share more information about the programmable power source? And second is that the second question was related to the crypto mining loads. So there was an unbalanced voltage set in the crypto load cases. So were those just temporary sags, or whether you observed sustained voltage imbalance on the supply side voltage?
Thank you for the question. I'm collaborating with Professor Prasad NJT, and his background is on power electronics, and he has this uh, computing load lab, and this is our programmable AC power source we can use to simulate the disturbance from the grid. At this case, for this AC, the power source, we can use this to program the AC source, voltage source, the profile of the AC power source, so that you can simulate the grid side disturbance. And in terms of for the voltage sag, we can they should have both the temporary sag or the permanent sag. So for example, in this case, we just simulate the voltage drop to 0.73 per unit, and then it can keep maintain at 0.73. So this is can last for a long time. And sometimes we can also simulate the voltage sag for just a few cycles. But depending on the protection, it can be tripped or can rise through. But for both the model and our testing, we have we have done both.
Yeah, this is Prasanna. I asked the question. So, actually, I was referring to one of your results slide. Like, if you go further down, there's a slide that showed you observed like unbalanced voltage sag on the three phases.
Oh, this
Uh,
case.
yes. So, were they just did you observe them temporarily, or did you actually notice that it was sustained over a long period, the unbalance due to the load?
Oh, this is real events data. So we get this voltage data
Oh,
from the DFR, the digital faults recorder.
okay.
So
So you,
then we
you don't know.
replace
Okay.
the voltage on the grid side, then simulates the power response from our model.
Okay, thanks a lot. And I'll send you an email regarding details about the power supply, the programmable AC source, the model,
Mhm.
and the capabilities. Thanks a lot for the questions and for the great presentation.
Sure, yeah, thanks.
Yeah, and there was another question about the crypto mining load. So, uh, s- uh, uh, Shu Wang wonder why the mining load is modeled as constant current load.
Why the crypto mining load is modeled as a constant power load?
It's constant
First of all,
current.
the power can be we can set the power reference because for the miner machine we can change the hashing rates. So different hashing rates is associated with different power reference. But we have also done testing for the miner machine. Their behavior is behave like a constant power load. So for example, if we change the voltage, then the current, if we lower down the voltage, the current from this miner machine will increase. Then if we compute the power, we can observe that the overall power from the miner machine at different voltage condition is kind of constant. So that's why we model the miner machine, the crypto miner machine as a constant power load. But this power can be the power reference we can set. So for example, in this simulation results, we have this software interface. We can change the power reference points. So for example, you can increase the hashing rate or you can increase the power from 1.5 to zero point 0.8. So then we can see the power change from the crypto mining load. This is the real experiment. Yeah.
Yeah. And there was another question related to the grounding. So how is the grounding modeled, and specifically how the one phase I2 rec load is aggregated into three phase, and how their ground paths are connected. Yeah, as the
Sorry,
questions from
I
Wei
didn't
from
see
Yan.
let me see the original question.
Yeah,
It's about the grounding. I think for the converter and also the source, as well as all those transformers, we have the grounding settings. But I don't really remember the technical details about the grounding setting. You can refer to our user manual for the details.
yeah. And the upcoming question was whether you tested your data center load model in a rear disturbance event, but I think you said no in your
Yeah, no, we
answer.
haven't done that. So we just
Yeah,
finished the model, but we are happy to collaborate with any data center operator or the utility or ISO to get the real data and to test our model and to see a response to a real disturbance event.
yeah. And another question was also related to the data center model. So the grid following rectifier model can the grid following rectifier control the grid voltage? It was the question from Muhammad. And actually, I also have a question related to this model. So whether is there any reason you selected the grid following control for the rectifier instead of the grid form control?
I think yeah, we can. So in this case, we set for the rectifier, it works as the double conversion mode. So mostly is to maintain the DC link voltage. So this DC link voltage to be a pretty constant value. So we have the power, we have the voltage control. So the rectifier mostly working in the constant DC link voltage control. But yeah, I think we can change the control mechanism for the rectifier to be also like the regulate the grid side voltage, especially if we have the battery here. We can use the battery to supply the power to have like the power support for the power for the power grid. But in general, I don't think data center they are doing this. So what they want to do is they just want to use the battery to supply their AI load computing. They will not use currently they are not using the battery or the UPS to support the grid. But I think technically, yes, we can use the rectifier to regulate the grid side voltage.
Thank you. Um, there was also two questions from Chinwei. The first question was whether you can elaborate more on your battery model. And the
Yes.
second question was why crypto mining load do not use the UPS.
Okay. Yeah. Thank you for the question. Here is our battery model. So here we have this DC-DC converter. This is the architecture of the DC-DC converter. And here we are using the PI control. It can be like the power control or the DC link control. For the specific battery, I think it's a module in PSCAT. We directly use the battery module from PSCAT. What we do is we implement this DC-DC converter as well as the control mechanism. For the second question, crypto mining load, because crypto mining load is not very critical, they can just shut down their facility if they want. The mining process, they can be interrupted and they will not really lose the data or something. So we say the crypto mining is like some very flexible load. They can change, they can wrap up, they can shut down, they can start up. So they don't need a UPS. UPS is very expensive. They don't have a UPS to maintain the constant power supply to their crypto mining loads. They don't have to do that because it's the mining process is not very critical.
Yeah, and we have two questions remaining. The first question is whether the researchers can use your model to analyze the control interactions between renewable inverters and the fast acting dynamics of data centers.
Yeah, I think so. So for this model, one of the use case I think is to connect this model with the grid model. For the grid model, we can have the renewable inverters, we can have the synchronous generators, and to see the overall interaction.
Yeah, and the final question comes from Ahmed. Ahmed, if you have any your question, I think you can turn on your mic and ask.
Yeah.
For the cooling load is currently we model with I think we have some details in the last slide here. Okay, yeah, here's the cooling load. We model as a rectifier connecting with the inverter and the induction motor. So this is our modeling for the cooling load. So for the rectifier converts AC to DC, and then the inverter converts DC to AC. Then is the variable frequency drive based induction motor to model the cooling load.
So yeah, thank you, Chen. Yeah, I'm Ahmed Saber from ETAP. Okay, can you hear me?
Yes.
Perfect. So yeah, just I'm curious. So for the cooling system, I believe is it liquid cooling or let's say any cooling, liquid cooling or not liquid cooling, HVAC system. So the mainly the power depends on the pumping system or also the chilling. You have considered both, or what should we consider?
No, currently we only have a model as an induction motor, and usually for a data center, I think they are using liquid cooling or at least hybrid cooling, but for crypto mining, they are using air cooling. Here we just use an induction motor. This is a typical induction motor, and we can set the load to the induction motor, the power to the induction motor as a reference. But we don't really model the pumping power or the chilling power.
So this induction motor, what? This induction motor because of the chilling, the cooling of the liquid, or what? Or not for pumping?
You can think of it overall, like the overall motor for both the pumping and cooling.
Okay. So okay, one more thing, that do you have any idea that how much power it consume for cooling or cooling system, and how much for the AI or the training or other thing? Which one is more?
So in data center, there is a metric called PUE, power effectiveness, power usage effectiveness. So they use this metric to show how the percentage of the computing and cooling load. It really depends. I think some typical numbers is like 60 to 80% is for the IT computing, and then probably like 20 to 40% is for the cooling. Depends
Okay.
on the specific data center.
Okay. And so your induction type load you used, that is very close to only the chilling part, not
Mhm.
the pumping part, right? So you don't cover the pumping, because for the pumping also we need some power. I don't know. Well, so how we can also use,
Xing,
or how?
sorry for interrupting. Maybe Xing, would you mind put your email in the chat box? So maybe, you can follow
Yeah.
up
Mhm.
because we might need to stop at some point for the
Yeah, given
hour.
the time, we
Yeah,
can chat
sorry.
offline. Yeah, no problem. Yeah.
Yeah,
Yeah,
yeah. I
feel
know
free
you
to
put it
email
probably.
me, right, if you have any question about the models.
Yeah, sorry. I think you have it in your slides, but please, definitely reach out to Professor Chen for more questions or follow-ups if you have more questions. Yeah, but very nice presentation and really impactful and timely work. And I think I came across that your career award recently, and congratulations on the NSF Career Award. And
Yeah,
keep on
thank
doing
you.
the great work. Yeah, thank you.
Thank you. Yeah.
Yeah.
Feel free to email me if you have any questions or any comments on our model. We are happy to adapt the model or keep polishing the model to better fit the real industry practice.
Yeah, thank you. Minsong, would you, maybe, I think we haven't mentioned that, but we're looking for more speakers coming up for the monthly webinar series. Thank you, Xing, so much for being our webinar speaker today. And if anyone else wants to present their work and share new results, please reach out to either Minsong or me. And we really love to continue the discussion around this this important direction. Thank you all.
Thank you.
Thank you. Bye.